let's start. So we are happy to have Benjamin Doyon, who will give 2 lectures on generalized hydrodynamics and something unusual in the diffusive scaling.
Yes.
So the next one is next week, Monday.
Okay, great. Thanks. So it's a pleasure to be here to give this lecture. So yes, I will discuss the hydrodynamics of integrable systems. So 2 lectures. The first lecture will be the hydrodynamics at the Euler-scale, and second will be at the diffusive scale. And so the first bit of the lecture will be a lot of review for many of you, but still I'd like to do it to have implementations in the concepts. But I will explain some of the recent results also that are available at the Euler-scale. And the next lecture, diffusive scale, so it will be, I mean, there's a lot of new recent results on this, which I think are quite interesting and go beyond the integrable systems, like they go beyond integrable systems. And in fact, a lot of the stuff that I will say also is not just for integrable systems, but more general. So I start with the context, right? So what I'm talking about are integrable systems. Now there are many possible types of integrable systems: quantum chains, classical, cellular automata, gases or particles, quantum or classical. In principle, what I'm going to say applies to all of that, at least at the Euler-scale. At the scale, then I don't know. But I'm going to concentrate on classical systems for this lecture, and even on very simple examples, essentially concentrating on the hard rods examples, where things are a bit more easy to see. Okay? So what I have in mind is some Hamiltonian of particles in position and momenta. And the basic example, I mean, the Toda model is one example, and you've seen I think a colloquium on that by a model on Monday. But another model part of that is the hard rod model. The hard rod model, I'm talking about Hamiltonian, is simply the hard spheres, but in 1D, where you have rods traveling on the line with different velocities, which I'm going to call theta 1, theta 2. And what they do is that they are hard, so when they enter a collision, they just exchange the momenta, the velocities, and then continue forward. Right? So that's the hard models. Now, what I want to do with these models, I want to do hydrodynamics. In order to do that, I have to discuss conserved quantities. Right? So these models admit a number of conserved quantities. Typically, the Hamiltonian is conserved. This is a model of gas and particle. The momentum will be conserved. The number of particles is conserved. If it's integrable, then you have infinitely many more. Okay? So you have conserved quantities. I'm going to denote them by capital Qi. I denotes which conserved quantity I'm looking at. So Q0, for instance, is usually my number of particles, and Q1 momentum, Q2 energy, and Q3, Q4, Q5 are the higher conserved charges of the integral model. Okay? But you can, parameterize them in a different way. And for example, actually, in the hard rod model, all the velocities, which I denote theta here, are conserved because they are just exchanged under interaction. Okay? So in fact, you can consider Qi as being simply the sum over all the particle of a delta function of theta n minus theta I for given theta I. And in fact, well, if I do my hard rod model on a computer and distribute the velocities according to some distribution, I'm going to have a continuum of velocity. Right? So in fact, I'm going to have a continuum of conserved quantities, and I can just ask for how many particles there are which have velocity theta. So some of n that. So this is a continuum of conserved quantities in the hard rod model, but in general, I will have a discrete set. Okay, so conserved quantities, they have this form. Now, I want them to be extensive conserved quantities. So what does it mean, extensive? Well, it's kind of a non-trivial set in general, but for my purpose, very simple. What I'm saying is that the conserved quantity, say again, the generic index I, can be written as an integration over space of some conserved density, y of x, some local conserved density, y of x. So this is an observable in the many-body system that just observes what's happening around the point x. Okay? For example, Qi of x, IV, sum over all the particles, delta function x minus n times, so Q0 of x will be the density of particle is that, well, Q1 of X, like sum over N, delta X minus N, times Pn, where Pn is the momentum, in the case of the hydra that denoted by theta. And more generally, Qi of X is going to be the form of integral one like that, with that X minus N, and some function that depends on the X's and the P's, but which is kind of local enough around Xm. So it doesn't depend on the X's or the P's, but the particles that are far from Xm. There's some kind of a range of okay. So this is local conserved densities, and my conserved quantity should be writable as integration of the space of local conserved densities. So that's the setup that one needs for hydrodynamics. Any questions about this? Yes.
What are the P's?
So, sorry, so the P's are my momentum, the Hamiltonian, and in the hydrods, my theta I, theta n are the Pn.
Okay.
Just because it's because I'm going to use theta for the asymptotic momenta, and on. In the hydrods, the momentum at any time are equal to the asymptotic momentum, but in general, they might be different.
So suppose F contains xn plus 1, xn plus 2.
Yes.
What do you do? Still not obvious how.
So what you, it's kind of not completely obvious, right? But what you need is that there are a bunch of conditions you can impose on F for this to be proper local conserved quantity. In particular, F, if, for instance, it can be sum over all the particle of potential of xn minus xn, right? And okay, let's get example. Another example. For the energy, suppose this is the generic Hamiltonian system, right? Sum over the particle Pn squared root 2 plus sum over n and m potential that depends on n minus. Okay. This is a typical example, and the hydrods is one example of that, where the potential is very sharp, for asking the particle to be a distance a from each other. Okay. Now, what would be the energy density? Is what I look to energy density. Well, I can just write erase this f. Then instead of f, I can write Pn square root 2. When I integrate over x, that gives the function that gives the right thing, plus sum over n potential of xn minus x. When I integrate over x, gives the function that has the sum over n and m that produces a second term. Okay? For example. Now, what I'm saying to work, the potential should be local, should have local interaction. So imagine that the potential goes to 0, say, at large distance. So this is local because when for every particle x that is far from xn, potential is 0, so this doesn't depend. That's an example of local potential. Now, it's not a kind of, maybe one should call it quasi-local if the potential has some slowly decaying, some decaying tails and all that. It actually depends on how the particles, right? General, but not very much on the particles that are far from each other. That's the type of thing that I'm looking at. Yeah? Other question? Okay, for the hydrods, because I can think of a continuum conserved densities, I could write q theta instead of I q theta of x very simply as sum over n delta x minus n delta theta minus theta n. This reproduces the local conserved quantity. It's local at x equals xn. It's very simple. Just as you, it just looks on the phase space of the hydrods, if there's a particle at x comma theta, comes out these particles. Okay. So this is an example you had of more generally is going to be things like that. Other questions? So this is context. So you have conserved quantity extensive, you have conserved density. Now, what do you do with that? So what do you do that? The first thing is that you should write down or consider the conservation law. So this is conserved quantity. Qi is conserved, so Qi dot equals 0. And so there are certain currents, and this appeared also in Patrick's talk Tuesday. So essentially, in general, this implies, or now many examples, is connected to observation of total quantity is the fact that there is a local observation. So there exists current such that dTqi plus dxqi. Now this is time evolution, say with respect to this Hamiltonian. So a time evolved the observable with respect to the Hamiltonian in the yes.
Didn't understand why this the derivative of Q1 implies that there exists a.
It's not so secondly that direction is okay.
Okay.
The other direction is not completely trivial. In certain situations, you can show that the integrable current must exist of current. Now, the general idea is that suppose I do q dot that. Okay, so I have an integration over x of q dot qi dot. So this is, and that whole thing should be 0. But this is a sum, well, of local observables, which are supported on different points. There. But they're supported on different points there, essentially all independent. The one that is there cannot, not very easily cancel the one that is there. The cancellation should be in a local way. Like the one that's there should cancel the one that's nearby. The only way that this happens is that if q dot is the derivative. That's the idea. Does that make sense?
It's a kind of detailed balance condition or something like that.
I don't know if it's the detailed balance condition. Is essentially you say, so if the integration of a local observable in the model equal to 0, then this local observable must be a total derivative of some other local observable. That's what we need as part of the structure of the Hamiltonian system. That must imply this. The word is this is a sum of things supported on different points, and how can this be 0 if this is not local, then there's no place it's local. How can this be 0 when the one that is at x very far from the one that's at other x don't talk to each other are independent? Then somehow the only possibility is that. Proof.
You're restricting to one dimension.
Yeah, here in one dimension, similar ideas in higher D actually. It's not higher. Similar idea here in higher D, where you have a diagonal. Other questions? Okay, so this is the situation when we have it. For the hydroids, you can write quite explicitly what these currents are. Explicitly, and it's just from dynamics. Now, what do we do with that? Okay, what do we do? So the first thing to do with the hydrodynamics is the thermodynamics. So I have a dynamical system particles interaction. I want to do thermodynamics. What does it mean thermodynamics? I want to construct the thermodynamic ensemble. That's the basis of hydrodynamics. First thing you have to consider. What are the thermodynamic ensemble for instance, the ground canonical or the macro ensemble? You're going to have, say, integrate overall phase space and put some kind of Boltzmann weight. Now, the generic Boltzmann weight for Doyon is like the Gibbs ensemble, which would be something like minus b by h. That's the perfectly fine symbol for this many bodies. But in fact, I have other constant quantities. Right? And proper way of doing here is to consider the sum of all the constant quantities and some associated temperature or generalized temperature to each of them. This is called a generalized Gibbs. For integrable models, people have studied that. And why people have studied that? Well, basically, if you start with a state which is not equilibrium, some generic state, and you let it evolve for a long time, people observe, at least numerically, you observe numerically that the system tends to a state which is of that form. So this is given symbol, these are the typical equilibrium state that you will find. Now, if there's a finite number of constant quantities, then right, makes sense. If there's an infinite number of them, then you have to be careful what you mean by the sum, and some details here. In the hydroid model, you can write it quite explicitly. You have integration over position and this momentum now, which I theta, you have the conditions that the two neighboring particles should also always be at a distance greater or equal to the length of the rod, which I think I'm going to call A. A. And then you put this thing there, but you see here my constant quantities are of that form. So instead of a sum over I, but version of theta, and instead of beta I, a function of theta. And so the measure is going to be sum over all the particle. This function of theta, if I put that out of theta. So that's the generic equilibrium measure. It's determined by a function, not just a set of parameters, full function of one parameter. Okay, so this is this is the macrocanonical ensemble, and it's sufficient for do. Now, in this macrocanonical ensemble, you may want to calculate various things. This is the measure. What do you want to calculate in this measure? Well, you can want to calculate, for instance, the average. So the average of the constant density, for instance, right? For these beta, given beta, function beta, right? Or the average of the constant currents for this beta. Okay, so this is applicable to the action.
So you have n in the number of particles,
Yes.
but Q is a conserved quantity. So your function beta. Huh?
Yeah, I want to take n to infinity. So
Beta than
yeah.
you could twice the number of particles in beta.
I mean, you see, if I take beta equals 1, function 1, this is mu, this is mu times number of particles. And indeed, you will say, well, if my number of particles is fixed, so yes. So I mean, it doesn't matter too much. Eventually, I want to take n to infinity and volume to infinity. Right? I have the volume as well, which I haven't even talked about, right? I mean, on the line, if it's on the line, right? And indeed,
So you fix the density or you do grand canonical?
So it doesn't matter too much. I can do whatever ensemble I'm looking at local observables, so I'll be the same. But indeed, when I calculation, I prefer taking in terms of grand canonical, where I sum over all the particle number and put the volume, chemical potential, and take volume to infinity. And then, so here I will instead do sum over all the particle, 1 over n factorial, and then have this integration in x. And that thing, and that will be my average. And then the case beta equals mu, chemical potential is meaningful, because I determined where it is. So I can also, I could also, instead of that, discuss the microcanonical ensemble, where I don't integrate, I integrate with this measure, but in a flat way, but specifying all the concept of quantities to be within a certain shell, microcanonical. And then I take the volume, the shell small enough in terms of the density of the quantity. And then this is another ensemble. It all gives the same result for local term, right? So no matter the ensemble, give the same result. So when I calculate these things, the result the result does not depend on the ensemble as long as I make the right connection between the betas and say the fixed constant quantities. If you think about mathematics. Okay. So the point is that there are a set of ensembles parameterized by a certain number of parameters, beta i's or okay. These are the equilibrium ensemble function. Oh, but indeed, this is a good question. So the ensembles can be almost anything, but we have to know how we parameterize them, right? And here I'm talking about betas parameterize them, but I don't need to talk about beta. So we need to do this by qi bar. I can think about the constant of density themselves to parameterize my ensemble. If I know the average energy, the average momentum, the average number of particles, I have just 3 constant quantities. I know the ensemble. The coordinate and the okay. So, but then I can calculate various things. Sorry, the I bar. So this is function of beta. Now by general arguments of thermodynamics, I can invert that function. I can also write the betas as function of our q's by inverting this relation. And then I put that in here, so this also can also see this as current as function of our q. And in hydrodynamics, it's more convenient to think about the average density as coordinates for your ensemble. Once you know the average density, the average energy, momentum, particle, then you know the principle, the betas, you know the ensemble, and it doesn't matter even how you write the ensemble. Grand canonical, macro-canonical, it's a unique ensemble. Questions? Yeah?
Using homogeneous state or what?
Yeah. Here is homogeneous state, right?
When you write this thing here.
Huh?
Homogeneous space?
So yeah, there's no x dependence, right? Here, I didn't put the x, no x dependence, I put the 0, any position to say it up, yes. Yes. This is kind of thermodynamics, basic thermodynamics. I'll look here, I haven't calculated anything explicitly, but this function, qi of beta, or q theta of the function of theta, can be evaluated exactly in the hard There's a explicit formula in the hard for that. And likewise for this, sorry?
So infinite volume.
In the infinite volume limit, in the infinite volume limit. So yeah, so everything infinite volume limit with the finite density of particles. It's a gas. Okay, so yes. Now the other thing that I can calculate is some stuff that Patrick introduced in this stuff. One of them is this A matrix, something called the flux Jacobian, and I introduce it just because then I'm gonna use it in some context, and it's just the derivative of the average current with respect to the average density. Meaning you calculate the average current function of beta function of the average density, and then differentiate that. And likewise, this other matrix I think Patrick also introduced, it's covariance matrix, J, which is the derivative of the average density with respect to the beta that's in there, the macro-canonical ensemble. And this is the average of the total conserved quantity J times the conserved density I at the point 0 connected in the state beta. This again is something that you would want to calculate. It's not necessarily easy to calculate in a given model. Right? This is something that requires a bit of work, but there is a formula in the for that. These are two of the matrices that are fundamental in this. Okay. Question about. Yeah.
But it's still homogeneous or maybe?
Yeah. This is not homogeneous. So I can put it at any position. Yeah. Homogeneous infinite volume. So you may say, okay, infinite volume, right? Explicitly, right? It's the integration of the x, qj of x, qi 0 connected to beta. Infinite volume, this is infinite integral. But in these maximal entropy states, correlation functions, or two-point correlation functions of local observables, decay fast enough, such a way that this integration is finite. That's now why decay fast enough? Well, I mean, if there's phase transition, there could be some power decay, but certainly at large enough temperature is the case that they decay fast enough in one-dimensional system in many contexts to show that at any non-zero temperature is exponentially. Quantum spin change that's the case.
It should be.
Does that make sense?
Connected means that you subtract the
Yeah. Connected means quite specifically that is this qj x qi 0 in that state minus the product of x. J in that state, QI in that state. That was also it. Yeah. So in other words, the 2-point function not connected clusters that are just senses into a product of one component. One question. Okay. Now, what do we want to do with that? Now I'm going to introduce something inhomogeneous. Yeah. So, so let me consider some initial state, which is now not invariant of the time evolution. So these are invariant of the time evolution. These are constant points. Now let me consider some inhomogeneous initial state. But not any inhomogeneous initial state. I want this inhomogeneity to be on large scale. For the simplicity for the discussion, one can do many more things, but that will be sufficient. Okay? So for instance, typical one that one can write, okay, and I denote this with L. L is my large scale, it's curly L there. Okay? It's something which has both one way of the form. You still have a sum over i's, but then you put an integration over x. You put beta I, which are now a function of x, but slowly varying. So beta I of x over L. So these are fixed functions, but I put the large scale of x. And then I put the qi of x. Okay? So if this beta I does not depend on x, this is the same thing as that. Beta I qi. Same thing. That's great over all the space, I get all the charge. If it depends on x, this is not the same thing, and that's the example, not the only example of a slowly varying initial state.
So if you're in a hard rod, you could put beta of theta n and x.
Yeah. So in hard rods, in the case of hard rods, for instance, I would put integration over theta and integration over x. I would put a beta, not just of theta, but of x and theta, and my q theta of x. And indeed, q theta of x is a sum over n of delta functions, right? So that becomes exponential of minus sum over n beta of xn over L in theta n. That would be the equivalent for that. So these are just initial state. Now, because they're inhomogeneous, they're no longer invariant on the time evolution, just some initial state. Right? And I want to know what happens as a time evolves on some such initial state. Questions? So what happens? So the question is here, suppose I take an arbitrary observable. It can be a current, it can be a density, something else, but a local observable. Arbitrary local observable. O of x and t is local observable. The local observable that is evolved in time, and the local at x but evolved in time. So then I want to know what happens if I evaluate O of Lx, Lt in this slowly varying state. So there's one scale here, L. It's the scale of the initial state and the scale of where I look at.
So this is parameterizing your initial condition, right?
Yes, initial condition on the test. And all the time evolution I put in the observable. Like evolution with the Hamiltonian apply on the observable. And I want to know what happens with that. And here is the main thing. So if I take the limit L to infinity, the statement, which was not proven, but which is a precise statement, is that for every local observable, take the limit L to infinity, what you should find is the average of this local observable in one of these maximal entropy states. There is some beta there. But the beta that you find depends on this x and t. Depends where you look at the observable. So beta of x. So this is a statement of the hydrodynamic approximation.
Sorry, we don't understand. So initially you have an initial condition which has some beta.
Yes, and these are different betas. Yeah.
It's another one?
Sorry?
It depends on time.
Yeah. But your question is good indeed, because one expects, proven in some easy case, that this beta here that appears there at x and 0 is just the betas at x that I have there. It's the initial. Okay. But for time, well, it's the different betas. Statement is that there exists some beta so that this holds. It is non-trivial statement because it's a statement that should hold for every local observable. Okay? And so there are many more beta, no, there are many more local observables as there are betas. So this is non-trivial. If I was just asking the statement for every local density, then there would be trivial statement. Because there are many betas, there's as many betas as there are local densities. But there are more observables. And so if I ask for this, then I have a lot of constraints and just a few free parameters.
I don't understand the meaning of the last equation.
This one?
Yeah.
Yeah. So here, this equation defines what I mean by beta I of x and t. For all t greater than 0, defines that. Okay. What I'm saying is that, well, this equation also defines it if you wish at equals 0. So greater equals 0, right? Yeah. But I already had this beta without a second parameter. What I'm saying is that, in fact, if I define my beta xt like this, well, at 0, this equals that. Makes sense. I mean, it's kind of relatively obvious physically. One can prove that.
The error means L goes to infinity.
Yes.
And this beta
Correct, yes.
of xt depends also on the observable, right?
Sorry?
No.
What?
The beta of xt depends on the observable itself or not?
No.
No.
That is the non-trivial thing. Yeah, exactly. So this is true for every observable, local observable. That is a non-trivial statement.
An equation, beta.
Sorry?
There's some equation.
And then we have some equation for beta. For now, it's just this define the beta x. Everything is non-trivial. But then we want some dynamical equation for beta x, and that's the other equation. Okay? And I can argue for it just now, right? Other question. Okay, so this is the general statement. Now, indeed, what about the equations for beta? This defines beta xt, but it's non-trivial, but not so useful. Because then I have this whole space, betas everywhere in space-time, right? However, I remember that I have these conservation laws. Right? These are conservation laws that are valid microscopically, right? This is Hamiltonian evolution conservation law. And the idea, I mean, I can derive that in a kind of a trivial fashion, if you wish, right? And let me take this within the initial. This is true for every observer. I can take that within the initial state. So I average just within the initial state. So I put my initial state here. This is true. That's certainly true. It's just valid, for every initial state. Doesn't matter. Slowly varying on that doesn't matter. Now, because the state is slowly varying, most likely this derivative with time is small, or the 1 over L. And this one also is small 1 over L. Okay? But it doesn't matter too much. The idea here is that, okay, this is true. Let me now kind of evaluate that, rescale L, T and X, because the derivative of rescale T and X. So now I put an L there. I put an L there. And this is the ballistic rescaling, which is good because it's this same prefactor that appears there. So the equation is still valid. It's a homogeneous equation. I can do ballistic rescaling. And now that I have that, this is subtle, right? Because now this time derivative with respect to t, and t now is the macroscopic coordinate, not the microscopic one. So L is large, well, that's fine, right? Now that I have that, well, then I can use that limit there. Right? Naively just use the limit there and put it in here. So what I find is dt or the average of qi, which I have denoted qi bar in here, right? It's qi bar. It depends on this beta xt, so I can put xt there. Right? So this is average of qi in beta of xt. Plus dx of what I had denoted gi, and remember that I had written it as gi as function of the q's, function of the q bar, okay? Gi as a function of all these q bars out there, that all depend on x and p, right? equals 0. Okay. So this is in the average of the I in beta of xt.
So the meaning of this is what? You have a function of a parameter beta, and
Yes.
then in this function you plug beta of xt.
So yes, yes,
It's not a functional.
yes, yes.
It's
So
not
it's
a
not function of the exactly. This is function of all these betas, and I plug beta
It's a
xt.
simple function.
Very simple. Yeah, exactly.
Mechanically,
And likewise here, beta xt. But I know that I have this relation between beta and q always, right? So I can, so qxt is just inverting that thing. And so if this beta xt, then I write it as a beta of the q of xt by inverting by this inversion, that becomes j of qxt. Station, right?
What does it mean, the bar below the beta?
So my upper bar is my average, and my lower one is because this is a many parameter vector. Vector. Yeah? Okay, So I have things like the Q upper bar, lower bar, vector of averages. And at some point I will use the bar on the right. Okay, another question. Yeah? All right, so now this is an equation for Q average, function of xt. And there are as many equations, all these i's, as there are unknown in the Q bar I. This is a fixed function of this Qi. And so I should put my on the bar, right? So these are the Euler-scale equations of the model. So these are equations for this Q bar that determine how they evolve in space-time. In principle, if you know where they are at time 0, then you just solve that and you know where they are at the time. Right? Principle. And once you know the Q bar, you know the beta by its inversion, and that determines this beta. That was the question. Questions? So now if you take a non-integrable system which has particle momentum and energy conservation, and if you use Galilean invariance, this comes back to the equation you will find in the textbook, or the equation and all that stuff. This textbook equation. But in general, integrable system is something else, and in general, this is the equation. It can be written in the quasi-linear form, which involves the flux Jacobian, where now you explicitly have with implied summations over repeated indices.
choosing J as the index.
Yeah, okay.
K.
K is better. Yeah. K is better, yeah. So you have with implied summation over repeated indices. This is linear in the derivative of Q bar, but not linear in Q bar because this A matrix. A is defined like that. It depends on the Q's, right? It depends on the state. In general. You can do all of this for a model of free particles, and then you find that A does not depend on the state. And you just find the velocity of particles. You can do this for the hadrons. A depends on the state in a specific way that you can calculate that. Otherwise, now, you remember in Patrick's talk, he was saying that this A matrix, the spectrum of the A matrix is a set of number, which I use VF, V maybe, set of number I. So the spectrums A matrix are, in fact, the hydrodynamic velocity of the model. That you can see by doing a linear perturbation of this equation. So you assume that your initial state is really flat except for some little bump somewhere. Then you see how the bump propagates. And if you write that, you will get a linear equation for the propagation for the little bump, which you can diagonalize. This R matrix, R matrix, right? And when you diagonalize, you see that this little bump they propagate with the eigenvalue of the A. As a probabilistic general stuff. Okay, so that's the solution. Question. So this is the general construction, and it turns out in integrable systems, particularly in the hadrons, everything can be calculated. So what do we need to have the hydrodynamics here? We need the main thing that we need, the only thing that we need at level here is this function J. Once we have it to put it in, and we have the Hydro equation, okay, J of Q. That's what we need. Well, actually, we also need to know what are these Q's, but okay, we know for the Hydro. The Hydro is the Q theta that I introduced now. Okay? But then we have this one J of Q. Then we have the Hydro. Okay? So for the Hydro, we have this Q theta, so we had all these local densities, and I'm going to denote them. So their average in some maximum entropy state. I denote it by rho of theta. So just patient standard notation. And so then Q bar, I of x and t, what it becomes is a rho of x, t, theta. Theta is what we place the index x, and xt is going to look at the state at position xt according to this equation. Which you see, the picture is here, you have your x and t there, and then everywhere you have some beta of xt, or you have some q bar of xt. So you have different state depending where you look at. And the physics, I didn't say anything about this, but the physics is that after a long time on large scale, things thermalize microscopically very quickly. And while the conservative still they move very slowly. So there's this separation of scale between what thermalizes fast and what moves slowly. And this is the local thermalization principle, right? Local entropy maximization. Things that go very fast, things that are not conserved, thermalize, and then local conserved quantities move slowly. Okay, so how do I do that? So I have this rho x theta. So then I want something like dt of rho of x theta. Density of rods around point x theta in phase space at time t, plus dx of that curve. So j bar, which now depends on theta, and it's a functional of rho at x t. That's the equation that I have for the Hamiltonian.
I'm still a bit confused. There was a beta on the left-hand side, it disappears on the right-hand side.
Yeah, because you see, the beta is just there's a relation between the beta and the q bar, right? That is 1-to-1 relation to q bar, and this is my q bar, Right? And just the beta here was a function beta of theta in the hadrods, right? So there's a functional relation between the rho and the beta, 1-to-1 relation. I'm using rho instead of beta. Of course, rho depends on beta, but this is the coordinate that I'm using, so you can forget about beta. Make sense? That's kind of
More or less.
the 1-to-1 relation between rho and beta, and so I'm kind of automatically using this 1-to-1 relation. So then the currents, I see them as a functional of rho. The question is, what is this functional of rho? Okay, so now, and I should say this form and this rho x theta, this is valid not just in the hydrods, but in integrable systems in full generality. The only thing that may change is what is the space of theta. Here for the hydrod, theta is just a real number, but in general, it can be something more complicated. It can be some additional structure to the space. So there's a certain manifold of that spectral parameter. And the question is to determine what is this manifold of theta. Yeah. And physically, the theta corresponds to the asymptotic state. You have your many-body system, and you look at what happened at very large time. It separates into asymptotically, freely propagating particles or solitons or objects. Right? And this theta parameterizes these objects. In the hadrods, it's just the rods with their velocities, but in general, it can be solitons with different velocities, or particles with different velocities, or different particle types. Yeah.
Do you know the integrable model or the singularity in the relation between beta?
I don't know. It's a good question, but I do not know if there's any of that. So this has to do this relation between beta and q.
Because then we produce shock.
Yeah. So you can I do not know, but So this has to do with the positivity, strict positivity of symmetrics. And I don't know of general result that say that symmetrics must be strictly positive. So Patrick also has to discuss that a bit. But in all the examples that I know, it looks like it's strictly positive, and it's okay. But otherwise, yeah, otherwise there are problems there. Here, details there. Yeah. Another question. Okay, so what is this J bar? Well, so there is a picture of what this J bar is. And the picture is as follows. So take a rod theta. So you want to know the current of the mode theta. Look at the rod theta within a gas. So there's many other rods, that go around. In particular, the rod theta will hit at some point some other rod. So this is my special rod. There are many other rods. Yes. Eventually, it will hit another rod. That. Okay. And then it will change the theta. So this is a theta prime. And then this one will continue on the left, this one will continue right. Now I'm gonna, with my corridor, I'm gonna follow the parameter theta, not the rod itself, but the tracer. Now I continue like this. And then this continues like that. And this continues like this. Okay. That's really much, right? So what we see is that this rod theta has jumped after interacting by a certain amount. The amount is the rod length. Okay. Right? So if you look in the gas, your rod theta is going to do a whole bunch of jumps like that, followed by free propagation. Free propagation theta jumps A. And on the large scale, there will be overall some effective slope. This is the effective velocity. Well, I will denote it as Vf of theta. Turns out, same thing as that, but that's a posteriori one. For now, it's Vf theta. So one can write an equation for Vf theta by a simple argument saying that there is a certain density of the rods, so a certain number of jumps you will have, followed by interspersed with pre-propagation. And the equation is as follows. Now I'm going to write the equation in more generality than the hard rods, but to work for the hard rods. So it says that the effective velocity for particle theta is equal to theta, which is propagation, plus a modification because of this additional jump. And the modification has the following shape. So I'm going to write it like that. Then I'll explain the tempo. There's an integration over the other particle, the alpha. So these are the other velocities, the other thetas, theta prime. Okay. There is a density of the other particle, rho of theta prime, because the more they are, the more jumps they are. Okay. And then there is the jump, and denoted phi of theta prime. This is equal to minus A for the hard rod. Okay, but this is more general for integrable system. Okay? So minus A. And then there is a probability that particle theta prime hits particle theta, right? Because the job is theta. And the probability is proportional to the difference of velocity. Because if they both have the same effective velocity, they will never hit each other. If they have different effective velocity, they will hit. And then you put the difference of effective velocity. V effective prime minus V effective. So this is the explanation of this equation. You work in the details a bit more, you know this exact formula, right? And you see that this is a linear integral equation for V effective. It is relatively easy to solve when phi equals minus A for the hard rod, you can write explicit. But in general, for the integrable system, is that what is phi in general for integrable systems? Well, in an integrable system, you know that you have factorized scattering theory where a many-body scattering event produces scattering shifts, which can be seen as occurring from a set of separated two-body scattering events. So when you have many particles hitting each other and out, is the same thing as two-body scattering there, two-body scattering there, two-body scattering there. So an integral model for a many-body scattering event, all you need is a two-body scattering to know everything. And this two-body scattering in classical models, what it does Wigner shift of your particle or your photons. So this two-body scattering is what is there's some particle coming and then some interaction, perhaps something in a Toda model is going to be something like that, say. And then if this has momentum theta 1, this has momentum theta 2. After that, you have a change momentum theta 2, momentum theta 1 with a certain shift. And this shift there is what I call phi theta 1 theta 2. In this formula, I'm assuming that it's symmetric. It doesn't have. So phi is the two-body shifts in a two-body scattering event of the integral model. So if you think about KdV, you think about solitons of KdV, you have two-body solitons scattering event, there's a shift which can be calculated. Toda model, you can think about the Toda particles or the Toda solitons, depending how you see that as two-body scattering shift. The hadras, this is the two-body scattering shift. But that's the general equation.
So for the soliton and the particle are the same thing?
Yeah, so this is a delicate point. The question is, what are your asymptotic states? Okay, let me take the example of the Toda model. Toda model, I didn't write Hamiltonian, but it's a set of particles that interact with each other in some exponential way. Okay? I can see that as a model for particles. Put a finite number of particles there, and then let the whole thing expand and see what are the scattering states. Scattering state would be just freely propagating particles. Now these are particles. And I can look at two-body scattering of particles, and then all my asymptotic states are particle, everything is the particle scattering. Or I can see that as a chain. So the particles are the nodes of the chain. And the infinite volume limit is not just putting free outside of the particles, putting many of these particles with a certain fixed density. Then the excitation there would be soliton, which kind of motions of this chain of particles, right? I think this is what I'm always working on. His paper, solitons, right? And now you can look at solitons interacting with each other and they will have different scattering. And depending which picture you take, you might have different scattering or you may have different description. But in any case, the thermodynamics and the physics should be the same. But so it depends on the model, it depends on what you are considering. In fact, it depends on the choice of vacuum. Set of asymptotic state depends on choice of vacuum. And choice of vacuum then tells you what the thetas are and what these phis are. Questions? Okay, so this is the effective velocity, and then the simple relation is that this j bar theta as a function of rho is nothing else but effective velocity, which we see is a function of rho. We are solving this linear equation. Function of rho, I put it here, times rho theta. So this was established quite some time ago in the hard rods, was well understood in hard rods quite some time ago. Originally, I don't remember who, but the first one certainly is formula that's found in Robert Spohn's book, and it was proven rigorously. Otherwise, that is the case. It was also more recently established in many other models, including Bethe and Zas integrable quantum spin chains, this equation, quantum field theory, and soliton gas. So this was established in the context of KdV soliton gas by again in the L in 2003. And then, so 2016 and onwards, from our work and other people's work, this was established in many other ones. So it looks like it works quite generally in integral model. Okay, and once you have that, then you put it in here, and this is it. This is the equation of earlier hydrodynamics for integral models. So it determines how the densities evolve. Hence, it determines how the local states evolve. Hence, in principle, you can evaluate every local observable of time, space-time point xt. Questions?
Sorry, the last point, the way I view it is that you know V effective, and then you substitute this expression for J into the equation, and that gives you a closed equation on rho, and that determines the evolution of all of them.
Yeah, exactly.
So, so V effective always a function of rho.
Yeah, is a nonlinear functional, because this is a linear integral equation for VF, but once you solve it, nonlinear functional. Then you can ask many questions about that equation. Maybe I just want to, my time is up, maybe, or can I take like 5 minutes to say something about that equation? So because you can ask about, okay, well, this equation is a complicated equation, right? It's nonlinear functionals and all that. Can you solve it? What happens with this equation, right? So it has a few properties, and I'm not going to derive the properties, but I just want to state them, right? So one of them is that there's a way to linearize the equation. Linearize it. It's a non-linear approximation, but you define a new coordinate dy, which is written as there's a 2 pi for standard normalization, doesn't matter too much. 1 plus integration d theta prime pi of theta prime rho theta prime dx for fixed theta. So you change your space, like you put a metric. It's a theta dependent metric. If phi is a negative, like in the hard rods, contraction of space. So what is this contraction? The meaning of it, if you think about the hard rods, the y, so the position x of the rod, so x1, x2, is mapped to position y's by contracting the rods to points. So this point, point. When you contract the rods to point, you take away the space that the rod take. Y1, y2. So this is effectively the free space that is free in which the rods can propagate. Okay? But the general transformation you can do not just in hard rods, in other theoretical models, and corresponds to the free space where things can propagate. In quantum theoretical model, phi is actually positive, so the free space is bigger than the non-free space. So particles, they get stuck a bit with each other, and then you can think of that as particles propagating in some kind of abstract space there. You continue to change the metric. And once you change the metric, you can define a rho hat dy by the idea that rho transforms as a density, rho hat dy dx, for fixed theta. Then it turns out that rho hat satisfies a free equation. dt rho hat of y p theta plus theta dx rho hat y theta is equal to 0. So rho hat satisfies free Euler equation for conservation of phase space.
Is it only for the hard rods, or it's more general?
In general.
More general.
Yeah. For any integrable systems, it's a consequence of this general structure. VF like that, now this equation is. So that tells you, that kind of tells you a hint that it's possible to solve this equation rather explicitly. For sure, this can be solved explicitly, right? It's immediate to solve. Just this y equals y minus theta t.
So the effective velocity has disappeared?
Yeah. This encodes all the effect of the effective velocity. This transformation of space. The idea. So, and indeed, in fact, it is possible to express a general solution to this GG equation and to show that the solution is unique and does not give rise to any shock under certain assumptions on the phi, under certain assumption. But I can write at least what the solution looks like, and this is a recent work with my student Friedrich Hübner, who was quite important in doing that. So you define a high field with a super defined with this, again, 2 pi is not one, but as integration of rho, say from minus infinity to x. You may assume the density goes to 0 at the very far in space. Though it's not necessary to assume that we can formulate things differently, but that's sufficient. And it turns out that there exists a function of hat that depends on two coordinates y and theta, which is strictly increasing in y, which has Gauss property, such that n satisfies the following equation: is n hat of x minus theta t plus integration theta prime over 2 pi theta prime times n of x theta prime comma theta total. So n equals n hat of something that involves n comma theta. This is a fixed point problem for n. And it turns out that if integration phi theta prime is small equal to 2 pi, and some other condition, some condition on rho. So rho, something like rho should be smaller than some rho max. But I can write this a bit more precise way of writing it. But this condition on the density cannot be too high. This condition on density. If this and that, then it's a contracting fixed point problem. So there's a unique solution. So what I'm saying here is that this is equivalent to G, the equation with that, the equivalence being obtained by doing this contraction. Solution of this is solution of the equation. And oppositely. And this, in certain conditions, has unique solution. So then you know you have a solution to your equation. It's what behave now. You can further show that there was we know this again in these conditions. There will be no discontinuity that develop over time. So if you start smooth, stay smooth in X. And so it's kind of nicely well behaved equation thanks to this contraction. So the contraction is something we established with Herbert Spohn and Takako Shimura some time ago, and this is work in myself. A year ago. Okay, so this is one property which is kind of important of this equation. Questions? So another, okay, and I finished there. But the final one, the final property, and this is for Pierre, me about that. Is the equation has a Hamiltonian structure. Now, I don't know how useful this is, but probably we can use that to establish eventually the integrability of the equation. But for now, we're not there yet. But there's a Hamiltonian structure. So that means that I can write rho dt rho as being Poisson bracket between a Hamiltonian and rho. This is not the original Hamiltonian of the model, and this is not the original Poisson bracket of the model, different one. What are these Poisson brackets? Well, something like that. The Poisson bracket on this rho has dynamical variables, and my phase space is space of functions of x and theta. Particular space, and we haven't specified precisely mathematically what should be the space, there's some kind of suggestion, but and the Poisson bracket is like this. So again, some factor, some normalization, there's a delta prime x1 minus x2 multiplied by, then there's some dressing of delta prime dressed, and I'll tell you what dressing is. So delta prime dressed theta 2 evaluated at x2 1 times some other function, which is occupation function nx 1, which I'll tell you what it is, plus delta prime resting at x1 theta 2 times some function x1 theta 2. So there's a bit more here of a jargon, GHD jargon, let's say, by the dressing and the end. These are standard things in GHD, and I tell you what it is. So n of theta is rho of theta divided by exactly what's in here, divided by 1 plus operation theta prime, rho theta prime, phi theta prime. So n is just change of variable, you rescale your rho in some way. This is the n that goes there. Dressing, when a function dress, is something that satisfies a linear integral equation similar to effective velocity, a bit different. Think of integration, prime, n of theta prime, phi theta prime times f dress theta prime. So dressing is a solution to a linear integral equation that involves n. N is and the interaction phi. And this delta prime theta of any function is just the derivative of the delta function. And so you see this as a function of one of the arguments which you dress, which is to the state. The state depends on x, which you put it in here, and then you calculate that. So this is the first thing, is that this is a correct Poisson bracket. So satisfy Jacobi identity is non-trivial to prove, which we can prove by using this construction. And it satisfies that you want, but basically Jacobi identity is the main one. And once you know this Poisson bracket, you can write the GG equation in that form, and it's very simple to write it in that form. H is not here, but equation theta squared over 2 rho x theta equation dx. So it's just the energy, total energy of the system, which is what this should be, right? I'm doing total energy. So total energy of the system with an appropriate Poisson bracket gives that. Now the Poisson bracket is nonlinear in the rows, highly nonlinear. So the n involves dividing by some row. The dressing involves solving an equation that has some rows in it, highly nonlinear. Okay.
If you have free
Sorry?
integrable system, you can find coordinate phase space for the solid and solid point system.
Yes.
And there is a Poisson structure in that
Yeah.
space.
Yeah.
Does it come from that one?
So I looked at your paper a little bit, indeed. So I haven't managed to make a connection, but yes, probably it's connected to that. Yes. It's connected to other stuff that people have developed in solid gas as well. They have constructed some Hamiltonian structure solid gas. Turns out some of this can also be written in that way. So this is surely. Yeah. In the case without any interaction, phi equals 0, it becomes linear Poisson bracket. And this is a known Poisson bracket that people have developed in different contexts. It's a known thing. So this is a generalization of what I've studied before. Okay. That's it. So thank you very much.
Other questions? Is there any example in 2D? Something like that?
It's a very interesting question. So we are looking at the KP hierarchy in particular. And so we think, yeah, that one can develop something like that for KP hierarchy as well. And there, the whole theory is much less developed. My understanding, I'm not expert in KP, but working with some experts.
But KP is 2D because
yeah, it's a
in
simple
system. You have an infinite number of coordinates,
yeah.
and you just declare that two
Yeah.
of these coordinates.
Right, exactly. So in a sense, trivial. I agree with you. Right? In a sense,
1D is very much 1D.
It's just taking the higher, the Hamiltonian of the hierarchy. So you see, here I said this is my Hamiltonian. I can take any Hamiltonian of the hierarchy and do the same thing. I just have to modify some functions here and there as the same. Then I can evolve in one and the other as well. So I will have many times. I think it's what is key. So then you can do that, but then you can start analyzing the statistical physics of that, the ensembles and all that stuff. And this is what we're looking into. So there will be something, but it's not as Denis says. It's a bit of a simple extension of that, just using higher Hamiltonian. Yes.
Other questions? Then it's time for lunch. Thank you.
Thank you.